everybody. In this lesson, we're going to learn about inverse functions. So the definition of an inverse function is basically the function that undoes the original function. So for example, if you had the function f of x equals x minus 1, the inverse function, which we write with an f with a little negative 1, kind of like an exponent, but it's not actually an exponent. But that's the notation for the inverse function of f. So the inverse function of f is going to be the one that undoes whatever f did. So if f takes a number and subtracts 1 from it, the inverse function would be to take the result of that and add 1 to it. So the inverse function undoes the original function. And you can have the inverse of relatively simple functions like this one, because if the original function has an input of 2 and gives you out an 8, or an input of negative 3 and gives out a 4, input of 1 gives out a 5, etc., then the inverse function is basically going to be the set where all of the x and y pairs are switched. Because the inverse function needs to undo the original function. So if you input a 2 into the original function and you get out an 8, then the inverse function needs to bring in an 8 and give out a 2. And so the inverse function of f in this case would be 4, negative 3, 5, 1, and 2, 0. So essentially, the inverse function just switches the inputs and outputs. And sometimes the inverse of a function is not actually a function. So in this case, we have the function f, where you input a 0, get out a 5. If you input a 1, you get out a 5. Input a 2, get out a 5. Input a 3, get out a 5. And this original function is a function because every input goes to one specific output. But the inverse of this is actually not a function, because if we write out the inverse of this, a 5 goes to 0, but 5 also goes to 1, and 5 goes to 2, and 5 goes to 3. And so the original function is a function, but the inverse of it is not a function because every input goes to multiple different outputs. And so if you want to test and see if the inverse of a function will be a function itself, you can do something kind of similar to the vertical line test. Because remember, we learned that a relation is a function if any vertical line goes through only one point. Because if you only go through one point with a vertical line, those vertical lines represent all of your inputs. And if they only have one output, then that makes the relation a function. And then an inverse will be a function, or in other words, we'll say that the original function is invertible if any horizontal line drawn through the graph only crosses the graph at one point. Because the horizontal line will tell you how many inputs are associated with an output. And then if you switch the inputs and outputs, then essentially that means that the function will be invertible, or that the inverse of the function will also be a function. And we say that functions are one-to-one if they pass the horizontal and the vertical line test. So there's one question on your homework where you're asked, is the function a one-to-one function? And basically you're looking for a graph that passes a vertical line test and a horizontal line test. So that's what one-to-one means. So let's look at some examples. So let's say that we had f of x equals 4x plus 5 and g of x equals x minus 5 divided by 4. If we wanted to know if g is the inverse of f, then basically we could say, well, does g undo f? So I could think about it and I could say, okay, well, if I put an x into f, I get this out as a result. And if g is the inverse of f, then that means that if I apply g to f, then that means that I will get back to where I started. So if I say, okay, I input an x, get this as an output. If I put that output into g, So if I take 4x plus 5, that's my output of f, and I apply g to it, so I subtract 5 and then divide by 4, if I get back to my original function, or my original input, then that means that g is the inverse of f. So if I simplify that, 4x plus 5 minus 5 will equal 4x over 4, and if I do 4x divided by 4, that just equals x. So you can use what we learned in our last lesson with composition of functions to test and see if two functions are inverses of each other. Because essentially what I was doing here is I took x and plugged it into f, and then I took that result and I plugged that into g. And so this would be g compose f, and if g compose f of x equals x, then that means that the two functions are inverses. Well, and actually technically you'd have to check it both ways. So you'd also want to check f compose g of x. So you'd put x into g, which gives you x minus 5 over 4. Then you would put that into the function f, so multiply by 4 and then add 5. But if that also equals x, then that means that f and g are inverses of each other. And in this case it would, because 4 divided by 4 just cancels out and you get x minus 5 plus 5, and minus 5 plus 5 cancels out to 0, and so you would just get x. So this is one way that you can test to see if two functions are inverses of each other. Now, most of the problems on your homework are where you actually have to find the inverse function. So I think you have a couple where you're like checking to see if they're one-to-one or if they are inverses of each other. But in most cases, you're going to be asked to find the inverse. So the way that you find the inverse is you basically switch the inputs and the outputs. So the easiest way to write this is to rewrite any f of x as a y, because usually we will graph the outputs of a function on the y-axis. So replace the f of x with a y, just to make it so that you don't have multiple things to write. And then you'll switch the inputs and the outputs, or in other words, switch the x and the y, and then you'll solve for y. And when you find that new equation, that will be your inverse function. So for example, if we were asked to find the inverse of the function that cubes a number and then subtracts 5, my first step would be to write this function rule where the output of the function is replaced with a y. So I'm going to write this as y equals x cubed minus 5. And again, that's just because we usually graph the outputs on the y-axis. Then I'm going to switch the x and the y. So I'm going to write a new equation where x equals y cubed minus 5. And the reason for this is because my inverse function needs to undo the original function, which means that whatever I input into the original function needs to be the output of my inverse function. So I'm going to switch the x and the y's, and I'm going to solve this new equation for y. So if I want to get y by itself, I need to get rid of the minus 5, and I'll do that by adding 5 to both sides. That gives me x plus 5 equals y cubed. And then the way that I get rid of a cube is I cube root both sides. So I'm going to cube root both sides, and that tells me that y equals the cube root of x plus 5. And so this new function is the inverse of my original function. And so I would say the inverse of f in this case would be the cube root of x plus 5. And that's how I would find the inverse of this function. And you can always test this out and see if I input this, or in other words, if I compose this function with this one. So if I take x cubed minus 5 and plug it into my inverse function, do I get x out? And in this case you would, because you would get the cube root of x cubed minus 5 plus 5. But if you do minus 5 plus 5, that would equal 0, and the cube root of x cubed would just be x. And so what I did back on this slide can be helpful for testing to see if your answer is correct. because if you compose the two functions that are supposedly inverses of each other, you should get your input as your output of that composition. So that's how you would find the inverse of a function like this. So I want to go through a few more examples, and these correspond to some of your homework problems. So if you want to open up your homework and find the problems that are similar to these, you're welcome to do that. So on this one, we have the function f of x equals x minus 2 divided by 3. So I'm going to start out by writing the original function with a y, and I'm going to write that as y equals x minus 2 over 3. Then I'm going to switch the x and the y to find the inverse function. So I'll say x equals y minus 2 divided by 3. Then I want to find out what y is. So to get y by itself, I'm going to start off by multiplying both sides by 3, which tells me 3x equals y minus 2, because this 3 and this 3 cancels out. Then I'll add 2 to both sides, and I get y equals 3x plus 2. And so that tells me that the inverse function of f is going to be 3x plus 2. Which means that this function undoes the original function. And if you want to, you could try composing these two functions to see if you end up with x when you compose them. But it's also pretty easy to see that this will undo the function, because if you take a number and subtract 2 and divide by 3, if you take that result and multiply by 3 and then add 2, you'll get back to what you started with. And so that's the inverse of a function like this one. You can also find the inverse of a really simple function like this line, because this function, if you were to graph it, it's in slope-intercept form, or y equals mx plus b. So if we were to find the inverse of this, we would say y equals 4/7 x minus 1. And then to find the inverse, I'll switch the x and the y, or the inputs and the outputs, and I get x equals 4/7 y minus 1. To get y by itself, I'll start by adding 1 to both sides, which tells me that x plus 1 equals 4/7 y. Then to get rid of the 4/7, I'm going to multiply the whole thing by 7/4, because if you multiply by the reciprocal of a fraction, it will cancel out all the parts of the fraction, and you end up with y equals 7/4 x plus 7/4, because if you multiply 7/4 by both of the terms, you'd essentially distribute the 7/4. And so the inverse function would be 7/4 x plus 7/4 in this case. If we wanted to find the inverse of this function, this one's actually kind of interesting, because if we rewrite this one and we say y equals 5 over x, and then we switch the x and the y, we end up with x equals 5 over y. And if we want to get y by itself, we should first get it out of the denominator. So I would multiply both sides by y, which gives me y times x equals 5. Then, to get the y by itself, I divide by x, which tells me that y equals 5 over x. And so this one's kind of an interesting function, because the inverse of the function is actually the exact same as the original function. So that one is kind of an interesting result with that. And then the last example I want to go over is how to find the inverse of a function that has multiple x's in it. So in this case, if we were trying to find the inverse, we'd start off by switching the x and the y. So I'll start off by saying y equals x plus 5 divided by x minus 3. And then you'd switch the x and the y's, so you'd get x equals y plus 5 over y minus 3. And if I want to get y by itself, then I first need to make it so I only have one y. And it's kind of hard to do that when it's in a fraction like this. And so what I'm going to do is I'm going to multiply both sides by y minus 3. So if I multiply by y minus 3 on both sides, that will cancel out my fraction, which will make this easier to work with. And that will give me x times y minus 3x equals y plus 5. So this is nice because I don't have a fraction anymore, but I still have two different y's. So in order to fix this, I'm going to get all the y's on one side and all of the non-y stuff on the other side. So I'm going to add 3x to both sides, and I'm going to subtract y from both sides. And what that gives me is xy minus y equals 3x plus 5. So now the y's are all on the same side of the equation and the non-y stuff is on the other side. But I still have two different y's. So in order to fix this problem, I'm going to factor out a y that they have in common, which leaves me with x minus 1, because both of these terms have a y in common. And this is going to equal 3x plus 5. Then to get y by itself, I'll just divide by x minus 1. And I end up with y equals 3x plus 5 divided by x minus 1. And this is my inverse function. And so whenever you're solving these fraction problems where you end up with multiple y's in your, like when you switch the x and the y's, if you have multiple y's that you're trying to solve for, basically start by getting rid of the fraction and then get the y's on the same side of the equation and everything else on the other side, and then factor out the y that the terms have in common. So actually, let's go ahead and practice this. So pause the video and try this one on your own to see if you can find the inverse of this function, and then restart it to see how I would solve it. Okay, so the way that you'd solve this one is you would say y equals 7x plus 2 divided by 3x minus 1. Then you'll switch all of the x's and y's, which will give you x equals 7y plus 2 over 3y minus 1. Now we want to solve for y and get y by itself. And so I'm going to multiply both sides by 3 minus 1 to cancel out that fraction. So I get 3 minus 1 on both sides, which cancels out this. And this gives me 3yx minus x equals 7y plus 2. Now I want to get the y's on the same side and everything else on the other side. So I'm going to add x to both sides and subtract 7y. And that gives me 3yx minus 7y equals x plus 2. So now I have all my y terms on one side, all of my non-y terms on the other side. And I'm going to factor out the y, which gives 3x minus 7 equals x plus 2. Then I'll divide both sides by 3x minus 7, and I get that my inverse function equals x plus 2 over 3x minus 7. And I would write this answer as the inverse function of f because this is the function that undoes the original function f that they gave me. And so that's how I would solve or find the inverse of that problem. On the first few problems on your homework, you'll notice that they have some graph problems. And so one of the things that's interesting about inverse functions is that if you look at the graphs of them, they're basically the same graph. It's just that the x and y axes have been switched. So like in this case, this one had a y-intercept of -5 versus this one had an x-intercept of -5. If we look at this one, you can see that this original function had an x-intercept of 2, but then it had a y-intercept of -2. It had an x or a y-intercept of like negative maybe 0.7 or something. And then the x-intercept on the inverse was negative 0.7. So essentially the graphs of a function and its inverse are the same graph, but the x and y axes are switched. And so on your homework, you're going to have some problems where they'll give you a relation or a function, and they'll ask you to find the inverse and then identify which graph is the original relation, which one is the inverse, and which one is neither of them. So what you would do in this case is you would first figure out what the inverse is by switching the x and the y. So like in this case, you would write it as x equals y squared minus 1, and then you would solve for y. So you would add 1 to both sides, which gives x plus 1 equals y squared. Then you would square root both sides. But when you square root something, you technically have to account for the positive and negative version of the square root. And so the correct inverse function would be y equals plus or minus the square root of x plus 1. And so this would be the correct inverse function. And then you would look at the graphs to see which graphs correspond to the original relation and which ones correspond to the inverse. So you would say like, okay, well, if I have y equals x squared minus 1, some of the things that make that equation true are 0 and negative 1, or 2 and 3, because 2 squared is 4, 4 minus 1 is 3. But also negative 2 gives you positive 3, because if you do negative 2 squared, you get 4, minus 1 would give you 3. And if we look at the graphs, it looks like this is going to be the only graph that has all 3 of those points on it. And so this would be the original function. And then you look for which one is the inverse. So if you want to, you could make a table for this, or you could also just switch the table of what you found earlier. So like you could say, if I input a 0 and get a negative 1 out in my original relation, then I should be able to input a negative 1 and get out a 0, or input a 3 and get out a 2, or input a 3 and get out a negative 2. And so the inverse relation would be this one right here, because this is where you input a negative 1 and get out a 0, or input a 3 and get out a 2 or a negative 2. So in this case, the inverse is not a function because it doesn't pass the vertical line test, but it would still be the inverse of the relation. And so this would be the original, this would be the inverse, and then these other two would just be neither. And so that's how you'll solve those problems. So that's everything for this lesson. If you guys have any questions, I'll be available on Friday to answer those questions. Or if you finish this lesson in time to come to my office hour on Wednesday morning, you can also do that. So I hope you guys have a great day, and thank you so much for your patience with my travel problems where I wasn't able to get to class. So thank you so much, and I hope you guys have a good day.